Unit 5, Impulse and Momentum. A lot of this unit is in fact dedicated to, as you would expect, momentum, which is given the equation momentum is equal to the mass of a moving object multiplied by its velocity. Momentum is routinely given the lowercase p symbol. And the majority of this unit covers collisions. Now, just like in the previous unit, we had the law of conservation of energy. Now we have the law of conservation of momentum, which is to say that the initial momentum of a system is equal to the final momentum of a system. And there's three very specific situations in which we apply the law of conservation of momentum. Number one, elastic collisions. Let's say that we have an object rolling towards another object. Object number one is velocity. Object number two initially has no velocity, it's standing still. And what happens in elastic collisions is that these two objects will collide, and afterwards they will not stick together. The equation that relates the motion of two objects in the elastic collision sense is equal to this. Yeah, we derive initial momentum is equal to final momentum, but then expand it out and relate it specifically to elastic collisions. I know that equation looks long, but it's pretty easy and simple. Mass 1, initial velocity 1, mass 2, initial velocity 2, is equal to mass 1, final velocity 1, plus mass 2, final velocity 2. Pay close attention to your negative signs for your velocity values. In this particular diagram, if you're moving rightward, you would be positive, and if you're moving, leftward, you would be negative. In addition to conservation of momentum for elastic collisions, we would also say that energy is conserved in elastic collisions. Energy is conserved, which means initial energy is equal to final energy, which in this case means this equation. That equation's long too, but it is still kind of simple. The first mass times its initial velocity squared, the second mass times its initial velocity squared, the first mass times its final velocity squared, and the second one. Notice that all of your velocity values are squared, so directionality no longer matters, because if those velocity values would be negative numbers, then they'll be converted back into positive numbers by squaring it. All right, the second application of the law of conservation of momentum. In elastic collisions, a mass runs into another mass, and the diagram looks similar as before, though more poorly drawn, but mass 1 will connect with and stick to mass number 2 in this situation. In this case, initial momentum is equal to final momentum, but the equation looks different because they'll stick together, as shown right here. Initial mass times initial velocity plus second mass times its initial velocity, and then the masses become combined and they share a velocity on the back end of that. You may be wondering about energy. In the case of inelastic collisions, energy is not conserved. So whereas before we did energy initial is equal to energy final, that does no longer apply here. Energy is not conserved in inelastic collisions. And the reason for that is more likely than not you've lost energy as a result of colliding with another object. Your velocity value is most likely dipped down. The velocity value has probably gone down as a result of that collision. All right, situation number 3, explosions. Explosions sound cooler than they really are. Sorry. We have 2 pass carts more likely in our lab that'll probably be stuck together or adhered together in some form or fashion, and then we take some sort of action that causes them to blow apart and travel in opposite directions. In this case, the equation that pertains to them is once again initial momentum is equal to final momentum, but unpacked it looks a little bit different than the other ones. There we go. They're initially together, so therefore they share a velocity. Now, more likely than not, just in real life, and if you're thinking about this, that velocity, isn't that going to be 0? And the answer to that is, yeah, it probably will. But it doesn't necessarily have to be. These two objects could initially be experiencing rightward or leftward motion at a constant velocity. And then something happens. And they, as a result of something happening, their momentums change because they become their own independent objects. They receive new velocity values, more likely than not. keeping a close eye on our velocity values for signs. If we're experiencing leftward motion, that needs to be negative, and if it's rightward motion, it needs to be positive. As before, with inelastic collisions, energy is not conserved. Energy is not conserved. More likely than not, if you're thinking about it logically, you've probably gained a lot of energy as a result of the explosion event. Next, with Unit 5, we'll talk about impulse. Impulse refers to the force applied to an object over the amount of time. Frequently, impulse graphs, if you can imagine it, go back to our work equals force times distance graph. Now we have force over time graph. So similarly, the area beneath the curve in the case of work equals force times distance, in this case, the area beneath the curve for force times time is equal to your impulse. And just like how work had a connection with energy, impulse has a connection with momentum. And in fact, we call that the equation, the impulse-momentum theorem. And it starts out with impulse is equal to change in momentum. Just like work was equal to change in kinetic energy, or change in energy, impulse is equal to change in momentum. Unpacked, that equation looks like this. And frequently it's used to describe the same thing as work is equal to force times distance situations. Let's say you have a box or you have a cart or something like that, and you're applying a force to that system over a given amount of time. And just like with the work kinetic energy theorem, same rules apply. You have your force, your time, and you'll probably be tasked with solving either final velocity or perhaps initial velocity. The reason why we pay attention to and study impulse and momentum theorem is that it has a lot to do with collisions and having safe collisions, or maybe perhaps not so safe collisions. Let's say that we have a block that's rolling along a frictionless air track with a certain amount of velocity. Let's say that it strikes this brick wall and is then brought to rest immediately. If you're diagramming that block's rightward velocity as a function of time, the graph might look something like this. All right, chilling out, doing the velocity. Brick wall goes to rest. The purpose of airbags and other such safety measures is to take this amount of change and maximize the amount of time. This is obviously the collision, and the more we can stretch that time out for that collision, the less force will be delivered. Because force times time is equal to change in momentum, and regardless the change in momentum will be the same, it began with a certain amount of velocity and ended with a new velocity. If the time goes up, then the amount of force delivered goes down, and it's a safer delivery of force. Looking at force on its own graph in this particular situation, you might see something like this. No force acting on the block for a good chunk of the time, and then all of a sudden we have a collision. The shaded area of the curve being equal to your impulse.